Okay, to all of you listening from home, sorry about that. We lost the recording. All right. So I think, I don't know what happened. I think maybe because I was accidentally switching screens with a 4-finger swipe, maybe it got confused. But anyway, here's our mmap setup. Okay, so before that, we actually have the size of the chunk. So here we have now the pointer that mmap gives you, points to there. Right, so put a little arrow on it. Okay, so that's helpful. Now we know how big was the chunk. So if anyone wants, so now we can stick that in a linked list. We remember how big it was, and that's fine. So now if anyone wants to allocate another chunk of the same size, they can have this one. But then we get to the coalescing bit. So say we get someone then allocates 2 chunks, and they happen to be back to back. Now we want to say, okay, we freed this one already. It's in some free list. Now we need to know what is the, and now we're trying to free this one. And ideally, you'd want to be able to treat this as one large chunk so that a larger request later on can be served by this free memory. So in order to do that, we actually need to know either what was the size of the previous chunk, or ideally a pointer to the beginning of this previous chunk. And so that gives us, let's do that. Yeah, okay, so now if we're freeing this thing, we need to be able to see, where's the beginning of the previous chunk so that we can put them all together. We also need to know if the previous chunk was free. Can hide that in a little bit in here. Although this only looks like this would be, oh, well, that makes sense. So here's 16 bytes, right? Maybe you could make a smaller size, but it's a little weird. Have a 4-byte size. Okay, so 16 bytes of this, and you want to allocate something, presumably more than 0. So I guess it doesn't make much sense to allocate less than 8 bytes, because everything should ideally be 8-byte aligned. So maybe that makes it 24 on its own. Another reason why it needs to be 24 is that when this is free, you need to put it in a linked list. And the linked list is a next pointer, a previous pointer, and a size. And there again, that's 24 bytes. I think 24 bytes makes sense. Okay, that's the sort of an aside, but it's good to know that malloc doesn't come free, so to speak. Okay, so it's virtually unlimited size. That's very nice. Maybe one other problem is that releasing large amounts of memory doesn't always work. Or freeing. So you could imagine if you have just a little allocation at the top here. Let me put a little one. Come on. And that one's taken. And now we've allocated a large amount of memory, and then we have a little amount of memory at the very top. And now we go and free this large amount of memory. We can't actually lower the break. We can't release that to the OS. And that's why we get this implementation of most mallocs that for a large chunk, they use an mmap allocated memory instead, which ends up being sort of a separate place higher up in the address space. Okay, so anyway, these two have both share the benefit that you can dynamically allocate as many as you want. Oh, here we go. Limited lifetime. That's a huge negative of the stack, right? If you allocate something on the stack and you return from the function, well, your variable is gone. You cannot provide pointers to those values to anyone except perhaps functions that you call. It's somewhat safe for functions that you call because, well, you're not going to return before they return. But if they then save those somewhere else, it can get weird again. So it's best to not pass references to stack values at all. OK, we have a couple other choices. You have static variables. It's only these are allocated at compile time, which means there's no overhead for allocation. But if they're initialized, they're allocated in the binary. That could be an issue. So if you have an array that's a gigabyte, let's say, you allocate it and you say equals 1 in curly braces. Actually, let's try that. Here's our program. It's a small program, but it's a big binary. And that's because of the compile time allocation of this program. So there's a this all ended up our array, which starts with a 1 and is all zeros for the rest. That has to be represented as a static value in the binary. Whereas if we change this to a 0, now everyone knows that if you mmap anything in from the kernel, it'll be full of zeros. So compiler isn't going to worry about assigning a 0. It'll just leave it alone. That's actually not going to generate any code, I believe. Let's see. Yeah, now it's 4 kilobytes. So the way a program gets loaded is there are all these little segments. Every segment gets mapped into memory wherever it says it should go. If we say, look at this. Some program, speculative, it's good. We have all these sections. Where are they? Yeah. So it says, OK, this part loaded into this part in memory. Oh, no, these are the sections. So it'll say, oh, my text, the code that we're running, started at this address. And it's, yeah, I don't know where the size is. Maybe that's the size. Maybe this is the address. I don't know. And then it says, for the read-only data, I wish I'd done that big thing on the Linux machine. Anyway, so it says for each one of these segments, the loader in the kernel will just say, OK, that chunk, put it here. That chunk, put it here. And the way a static array, statically allocated array, that's been initialized is declared as a huge section of those 10 megabytes of zeros. And so it's just mapped that part of the file into this part of memory, and we're done. That's why it's slow. Whereas this section here, the BSS section, says just map these things in. There's nothing in the file, but just give me this size, and it'll be all zeros coming back. OK, so if you get a program that looks way too large, that could be part of it. Beautiful thing, of course, with these is they're available everywhere. Globals are available everywhere, so it's really easy to work with. But for a multi-threaded program, basically, it's not going to work out for you. Okay, I like these static variables. Whenever I can, I try to allocate variables statically because it makes life easy in C. And then thread locals. We'll see that a little bit later, but thread local variable has a copy. You declare it like this. You say thread int count, and now there's a count for every thread as opposed to a single global count. So it's still a sort of a static, but every thread has its own, and they will be slower than most other variables, but they're still fine. Okay. Right. Okay. So I think because of the extreme cost of moves, in some cases, it pays off to pay attention to your memory allocation. And we'll try to see some examples of that going forward. I think there will be some in the homework as well. I can't remember. I'm working on the third homework now. So. All right. So, okay. So another thing that's happening in the CPU here, we were talking about this out-of-order execution. That's really useful when you have some instructions that go slow and others go fast. You can maybe try to do some work while you're waiting for a value from a slow instruction. But oftentimes, you don't know what to do next. So consider, let's see. Consider something like this. If parameter, some function parameter size divided by 100 is greater than 2. Then do something else. Do something else, right? So we talked about out-of-order execution here. If you just had this size divided by 100 up here, and then we had some other, do other work. Let's see. Slow instruction, do other work. Right. Out-of-order execution would probably execute this other work while waiting for the slow instruction to finish. But here, the slow instruction is in the if condition. So we're saying, if the result of this slow computation is greater than 2, then go and run this. Otherwise, go and run this. So out-of-order execution can't really do much. We need to know which one to run first. And that's where this speculative execution comes into it. So the CPU will actually make a guess. And this happens all the time. So here it'll say, well, I don't know what the size is, but last time we ran this if condition, last time we were on this line, there's actually, there's this comparison, right? And then usually there's a comparison and then there's a branch. So it's also called branch prediction. So last time this particular branch on that line of assembly executed, it was true. Maybe it's true next time. There's different branch prediction schemes, but that's probably going to be the most common one. So the CPU keeps an array, right? A little lookup table of, it's not an array. It'll be probably more like a hash table of the last 100 branches that we've taken, or 1,000 branches that we've taken. And it says, like, was it true or was it false last time? And if it was true last time, well, then we're going to run it as if it's true. Seems a little dangerous, because what if it's not true, right? So we need a lot of extra infrastructure to make this work. But basically, for each branch, guess which way it'll go. and execute speculatively. But don't save the results. That's the general idea. So we run these instructions, and we keep in our register reorder buffer, let's say, renaming buffer, let's say. So if we're just doing an add, right, the result will show up in this renaming buffer. We can mark it with a 1, or we just say, like, this is speculative. I don't know if it's going to be true. We can throw it out later. And we can keep doing that. That's all good. And then when the result finally comes in for that branch, then we can say, oh, yeah, whatever you did speculatively based on this branch is all good. So then we kind of retire those instructions. That's what it's called. The instructions that we had speculatively executed, they suddenly become fine. That was okay. But what about instructions that have side effects? What are some side effects you might have in, if we think about functional programming versus imperative programming, right? Sort of the same thing here. As long as you're using registers, sort of like you're operating functionally. Yeah.
If you are like memory mapping or something?
Easier than that, actually.
Loading something from the 30.
Loading doesn't really have a side effect, but storing does. Print is a system call. System calls are crazy side effects, like all over the place. And so you don't, well, actually it turns out that the CPU does speculate across system calls too, but it shouldn't. As we've noticed, perhaps if you read the headlines with recent exploits, there's all sorts of weird things that happen when you speculate across system call boundaries. But anyway, they're all performance related. They're not, supposedly, they're not correctness related. But if a program actually relies on performance for correctness, then it's correctness related. And so you can write programs like that that can snoop into kernel memory based on how fast things go. Anyway, that's an aside. Okay. The most common side effect, the one that we really worry about, is stores. All right, so we've made this branch. And it says, oh, if this is true, set global value equals 6. All right. And then what? Yeah. Oh, and here, print global value. Well, this will be fun, right? So we speculatively execute this part, and then it turns out, oh, no, that wasn't true. We're going to run this one, and now suddenly we're printing out a 6. So we can't have that. So in order to make that work, there's another piece. It's called a store buffer. So anything you store, when you do a move to memory, it doesn't actually end up in memory. It ends up in a long list of stores that eventually will end up in memory, but they're only released after the speculation has been proven to be true. Save in store buffer for later. Okay, so this is all pretty abstract. I thought I'd show you an example. Here it is. Okay, so we have a program, and now I had to do this with p-threads. Sorry, it's supposed to be single-threaded, but it was really hard to come up with a way that this becomes an interesting result without multi-threading. All right, so what is it doing? It starts up a couple of threads. We can ignore the interferer for now. I'm going to make sure it doesn't interfere, actually. Do like that. Aha, no, I had it on my... I have to figure out a way to make this more consistent, but I already had one on here. There, okay. Okay, so let's go back. What is this program doing? It starts up a couple of threads, an interfere thread that doesn't do anything at the moment, and a counter thread. The counter thread counts up, plus, 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 right? Until it's told to stop. And the main thread, well, it sleeps for a second, and it tells the counter thread to stop. That's it, and then we print out what was the count. So what's the count going to be? This thread, all it's doing is counting up. So it's reading from a global variable, doing a conditional branch, incrementing, and then doing it all over again. But reading from this global variable, we know that's going to take at least 4 cycles. Because it's at least it'll be an L1. Okay, so let's try running this thing. It's actually running 3.6 billion increments per second. And this is a 4 gigahertz sort of CPU. So it doesn't increment every second, even though it's reading this global variable. And the reason is that it's speculating. It keeps trying, it keeps incrementing, it keeps guessing that it's going to be true, right? It'll keep being true. It can just blow through all these increments, and then it'll probably say and then it notices after a while that, oh yeah, all of those were true. Right? It read once, yeah, they're all true, and then keep going over and over. Let's tell it to not speculate before we go. There's a way to tell it. There's another better name for it. It's called pause. Let's try that. Huh? Really? I think it may have eliminated that. Let's see. Ah, crap. What am I doing wrong? Aha, that's what I'm doing wrong. It didn't even change. So pause just tells the CPU, don't speculate past this line. That's it. It doesn't slow anything down other than that. And now let's run this. There we go. So without speculation, we're running 250 million operations per second. And with speculation, we're running 4 billion almost. And then we'll see what happens when it becomes false, but I think we're out of time. We'll do that next time. When the guess is false, it's much worse. All right, thank you.